Get ready to blast off into the incredible world of brain-computer interfaces. Neurocareers Doing the Impossible is taking you on a journey to meet the fearless pioneers pushing the boundaries of what's possible. In this special series, we'll be shining a spotlight on the nominees and winners of the International BCI Award, one of the biggest and most prestigious awards in the BCI world. You'll hear from BCI professionals as they share their revolutionary work and get a behind-the-scenes sneak peek at what it takes to be a winner. So, buckle up, grab a snack, and get ready to be amazed as we explore the impossible becoming a reality in the world of BCIs. But before we blast off, I want to give a big thanks to the co-host of this BCI Award edition on our podcast, Dr. Christoph Guger and GTech Medical Engineering. When I was a faculty member at the University of Cincinnati and Cincinnati Children's Hospital Medical Center, my team and I did some pretty amazing stuff for patients needing epilepsy surgery. We would put special sensors, also called grids, directly on their brain to prepare for surgery and create maps of their brain in a much faster and safer way than is usually done. It's called high gamma mapping, and it lets us figure out in just a few minutes the essential parts of the brain that need to be spared during surgery. Can you imagine? You can create a map of language, motor, and even math processing in no time. It was the first time this innovative technology was used at Cincinnati Children's Hospital Medical Center. When I moved to Florida, I established the first functional brain mapping and BCI program at Florida Hospital. I continued to use high gamma mapping to help epilepsy patients avoid losing their ability to speak or move after surgery. But even cooler than that, I created brain-computer interface studies that let patients control things with their brain in real time. Our patients could even spell words with incredible speed by just using their brains. No hands involved. I also discovered that brain-computer interfaces could help patients move their chronically impaired hands or legs years after a stroke when not much else could help them. So, I started working with the faculty from Advent Health University to help these patients restore their ability to use their hands. I received special training for it, and it's still mind-blowing how cool it is. My favorite part of what I do is teaching. At my established Institute of Neuro Approaches, I've integrated all my experience and knowledge into a unique course on brain-computer interfaces. With graduate neurobiology students, we started with theory, and then I gave them the BCI equipment so they could have hands-on experience working with BCIs. It significantly improved the way students learn, and they absolutely love this practical part of learning how to use neurotechnology. And all of this was made possible thanks to GTech's awesome brain-computer interface technology. They have everything from high-tech up to 1024-channel EEG systems to wearables, tools for neurorehabilitation, such as the medical grade system recoveries and educational kits with unicorn hybrid plug for learning how to work with BCI technology. But the most important part is their support and care. I have enjoyed working and collaborating with Dr. Christoph Guger and GTEC employees for over 15 years, and I hope for many more successful years ahead. So, if you are interested in GTEC's brain computer interfaces and neurotechnologies, check out their website at gtech.at. It's worth it. And keep in mind, I do not receive any financial support from GTEC and share my honest opinion supported by many years of experience working with their equipment. Dear Neurocareers podcast listeners, welcome to a special episode of the BCI Award Neurocareers podcast series, where we celebrate the brilliant minds and groundbreaking projects in the field of neurotechnology. In this episode, we have the privilege of featuring Colin Simon, the recipient of the BCI Award for his remarkable project, a multimodal brain-computer interface approach using muscle responses to transcranial magnetic stimulation of the brain. Join us as we dive into the fascinating world of Colin's research, where he explores the innovative use of muscle responses and transcranial magnetic stimulation in developing a multimodal brain computer interface. Discover how this novel approach holds the potential to revolutionize the field of neurotechnology and enhance human computer interaction. Colin will share the inspiration behind this project, the challenges he faced during its development, and the exciting possibilities it presents for neurorehabilitation and assistive technology. We will delve into the technical aspects of his work, exploring the integration of TMS and muscle responses in creating a robust and efficient BCI system. Get ready to be inspired and captivated by Colin's experience, passion, and dedication to pushing the boundaries of neurotechnology. Colin, it's a great pleasure to have you here today on our podcast. Can you please briefly introduce yourself and also let our listeners know where you are joining us from what part of the world?
Yes, hello. Thank you for that great introduction, Milena. I feel absolutely honored to be here now, and I'm almost blushing here behind my screen. So I am joining you today from Switzerland. That's where I am originally from, but currently I'm doing my PhD actually at the Trinity College, Dublin.
Maybe you can share some interesting facts about Trinity College in Dublin, what it is known for, what the program that you are involved in is about.
So in my PhD in Dublin, I think one of the great things that Trinity College is known for, but also what it does really well is the internationality of it. So I know, for example, that on my level, I'm on the third floor. There's so many people from different backgrounds and different nationalities as well. And it's really incredibly interdisciplinary. And I think that especially for neuroscience, this interdisciplinarity is a great boon. And it just helps because there's so many different aspects of neuroscience that are reliant on different methods or different backgrounds. There's cellular neuroscience, there's computational neuroscience. And yeah, in my floor, in my building in Trinity, we have people from all the backgrounds, from computer science, from cellular neuroscience, from psychology like myself. And so really the internationality of it is what I think makes Trinity a great place to study.
Wonderful. And you already mentioned your background in psychology, which is very interesting how with psychology background, you transitioned into neurotechnology. So tell us everything about that. How did it all happen?
Yes, I get asked this question a lot, actually, and I'm always a little bit surprised because for me, half of neuroscience is actually just psychology with a slightly different frame of mind. So for me, it was an absolutely natural transition. When I started psychology, I was interested in neurolinguistics. And at the time, I had the choice to choose a major in, or psychology was my major, but I could choose a minor in languages or in neuro linguistics. And at the time, I thought, well, it might make more sense to learn a different language so I get the firsthand experience of that. So I did choose Japanese instead of going straight into linguistics. And in the end, I think that was the better choice because I learned so many things, among them that neurolinguistics was not what I was interested in. It was still neuroscience, but not neurolinguistics. And as I moved on, I just got more and more interested in cognition, really. And that's what drove me to the very neuroscience heavy area of cognition. And from there, it was really just a little jump to go into what I would say that the first defining project of my career was my master's, where I worked on body ownership. So that is the study of why do humans feel that their body belongs to them? Because there are some very interesting cases where people stop feeling like their body belongs to them. And that was absolutely fascinating from a psychological perspective. And that's also where everything got a lot more technical because we were working with EEG heavily and with body temperature. So suddenly it wasn't really just about brains and thoughts and thinking about how we perceive the world, but it was suddenly very technical in measuring how people perceive things. From there, I got my PhD at the Trinity College Dublin, and that was really when it was full-blown neuroscience, where it was all about brain-computer interfaces and how to interact with computers and how to help with stroke rehabilitation. So that's how it got started.
Yeah, it's an amazing journey. And this work on body ownership, was this a part of your PhD that you were doing? Is that correct?
Well, that kind of depends on how you frame it. So, from a continental European perspective, that was my master's. So, no. But in the Anglophone sphere, the master's is usually part of the PhD or is not necessarily separate. So I did start a separate PhD in Dublin. The Human Body Ownership Project was back in Switzerland, in Zurich. But that's really where I got extremely interested in how we perceive and how we interact with the world and our body. And this is what ultimately led me to brain-computer interfaces.
Absolutely. And maybe it's not a direct topic of our today's conversation, but maybe you can provide a little bit more insights on this body ownership subject. You mentioned that there are conditions when people stop to recognize their body as their own. Can you maybe mention some of those conditions and what are possible theories behind that? Why does this happen?
Yes. So usually, or I would say the best described phenomenon is after a stroke, which usually damages the insula. So it's when the insula is damaged, then they can develop a condition called somatoparaphrenia, where they believe that part of their body, which everyone outside of them can obviously see is their body, but they believe it is not theirs, someone else's, and I think sometimes as well just not present at all. So when you see videos of that, and there are videos of that, although it is quite a rare phenomenon, you can see people steadfastly saying that the hand that they are holding in their own hand, so their hand, is, for example, their niece's hand, even though the niece is not in the room. So this kind of like this ownership of the body is a very hotly debated topic because there's lots of documented cases historically as well. And also it goes a little bit into this discussion of body integrity dysphoria, which is very closely linked to all the gender dysphoria topics. Although I think the scientific consensus is that it is a separate issue, but it is closely linked to that because it is about the rejection of one's body part.
I see. And Some people may not recognize their body parts as their own. Another question is, how can we recognize certain parts as our own? For example, if people are using prosthetic hands or prosthetic legs, yes,
Yes.
how they can start recognizing that as the part of their body.
Yes.
Is this also one of the topics that this field explores?
Absolutely. It is one of the best questions to ask as well, because there are so many cool findings. So just maybe a little bit about the neurobiology of it. So what we do know is there are neurons in the brain that are responsible for connecting movement, basically movement we see, movement we feel, and our own kinesthetic senses. So that means, for example, that when I move my hand, both my hand has a specific feeling, I can see it move, and that together in my brain is coded towards saying, oh, this is my body part because I effectuated this movement. I can see it moving coherently with what is happening. Part of my master's then was developing a setup, and obviously I had some technical help with that because it was very complex. But we did set up a virtual reality headset where people could see the real world. So the VR was not changing anything except for a slight time delay. So we were trying to get those neurons to kind of misattribute, because what people were seeing was delayed by a few milliseconds or half a second. And that led to it feeling very strange, because you could feel a little robot was touching you, and you could see the robot touching you when the touching had already stopped, and you could see the robot stop touching you, but you could still feel the robot touching you. So that felt very strange. And it's kind of a deconstruction of what is called in the body ownership field the rubber hand illusion, which is quite famous, where you put a mirror to the side of someone's face and then you touch their one hand while the other is hidden behind the mirror. And what you see is both your actual hand being touched, but also the other hand being touched. And then suddenly they introduce a discongruency. So, for example, what we do in the lab, obviously, is we take a fork and pretend to stab the hand, which is completely safe, obviously, because there's a mirror. But still, because you can see the hand in the mirror, you feel that it is yours, and you have felt the touch of the hand as well. So you feel that it is yours, and suddenly you're under threat, and you react to that, and it does feel very strange. And it's a feeling that I always thought it was a bit strange. You know, people report feeling strange, but until you have done it to yourself, you don't believe it.
Yes, that is an amazing, amazing field. And I'm very curious now, how did you progress from this to your project with transcranial magnetic stimulation? I'm sure there is some overlap between them.
Absolutely. So there's a lot of methods overlap, because we did use a lot of EEG. And we also were working with body ownership is in the field often worked with stroke patients, because they exhibit the most pronounced, but also the most predictable symptoms of somatoparaphrenia, for example. So I had some knowledge of stroke and what it meant to have a stroke, and some symptoms of the stroke and the disease overall. And also I had lots of experience with the method of EEG. And I think that's what definitely got my now supervisor, Dr. Kathy Ruddy, interested in me, because I could also work on my own with EEG, and I had some experience with MATLAB. So that was really, I think, what got me started in this field. And I was really interested in the transcranial magnetic stimulation bit. So transcranial magnetic stimulation is a non-invasive brain stimulation method where you switch on very powerful electromagnetic magnets for a very short duration of time, which changes ion concentrations in your neurons and gets them to be activated. So it's a way to activate neurons in the brain without actually touching or opening the brain up. So that's very interesting. And that is a method that is especially interesting for all sorts of illnesses and diseases where obviously the brain is affected in some way. So in stroke, where you have damage in the brain happening, TMS is an especially powerful tool to try and help those people.
Yes, thank you so much for explaining this. And now I'm curious, what type of TMS was that? Was it navigated TMS so that you can navigate to the specific region of the brain based on the patient's MRI, or it's more broad and general area that you were affecting? How did it all work?
So TMS, as I use it, so that is single pulse TMS, is most of the time quite precise. So it is not a whole target area that is stimulated. It is a very precise location that is stimulated. There's different things you can do with TMS. So it's not excluding anyone who does different work on that. But in theory, or at least what I'm using, is quite precise. So precise, in fact, that we target a specific muscle in someone's hand. So, and also as a caveat, I was supposed to do work in the hospital, but because of COVID-19, that work has been pushed back. However, my team is now very much working on getting into the hospital, and the work should start soon. So that's very good news. When we target a specific muscle with this type of TMS, we can get the FDI, so that it is the muscle in the hand that is responsible for the lateral movement of a finger, of the index finger in this case. And we can target this muscle specifically in the brain. We don't use neuronavigation tools because we can do that using motor evoked potentials. So a motor evoked potential is when we record the electromyographic activity in the finger. So that's EMG activity. Whenever we send a pulse through the TMS, the targeted muscle twitches, and we can move around on the patient's head with the stimulation coil and then figure out which spot produces the highest amplitude in this EMG activity. So it is quite precise stimulation, and we even target one specific muscle.
Yes, I can see. Now, as we already became familiar with the TMS and single pulse TMS and how precise it can be, can you describe the project that you submitted for the BCI Award? So now it's a combination, yes, of EEG, TMS. So tell us everything.
Yes, it's a combination of a lot of different things. The project overall is trying to harness the ability of what we call in the lab transcranial magnetic neurofeedback, or transcranial magnetic stimulation neurofeedback. I'm going to explain the individual little bits of the project. So TMS-NF is all about trying to make patients, or in our case also healthy people, be able to manipulate their response to the TMS stimulation. So imagine that we got you in our chair and we have targeted the very specific muscle, this index finger muscle. And whenever we send a stimulation through the TMS coil, we can make this muscle move. Now we would ask you, for example, to increase your response to this stimulation or to decrease it. So inhibition or excitation of basically the whole corticomotor pathway. So we stimulate the brain, but in the end, we would like to have an increased outcome at the finger movement level. So we're traveling here from the top of the brain, the cortex of the brain, through the whole spine and the lower brain levels to the arm where the twitch is then effectuated. And we have been able to show that this is possible, so that participants are able to increase their response to the stimulation and decrease it as well. And we're fairly confident that this is not the result from some other interaction with the whole experimental setting. So being able to volitionally increase the response to the stimulus is in itself quite interesting, but it is doubly interesting when you do know that TMS, especially single pulse TMS, can be used as a marker in stroke prediction, or the prediction of stroke recovery trajectories. So we know, for example, thanks to some work from Cafestinier, New Zealand, that stroke survivors, people who have had a stroke, when they come into the hospital, usually they have some kind of upper limb dysfunction, be that weakness or not being able to move at all. And this over time gets better, but we can predict when we do some stimulation or some TMS on these stroke survivors, we can predict whether or not they will recover well with some degree of precision, better than what we've had before. So one of the main criteria is if they react to the TMS, even though they have no volitional movement, but when we do the TMS, they have some response in the targeted arm, then that is a good sign. And for example, we do know that those amplitudes of the reactions just after the stroke, they tend to be really low. So you have to increase the stimulation intensity by a lot to get even a small response. And then as these stroke survivors recover, this, what we call MEP amplitude, goes up over time. So you need less intensity to provoke a response in the weakened muscle. So that's where you see the connection with stroke survivors. So one idea of this TMS and F is that maybe we can help those people who have had a stroke recover more quickly by helping them improve their reaction to the TMS, because we know this is a natural process that happens anyway. So maybe us being able to influence it will have positive results, or we hope at least. So that is the TMS and F part. Now, the problem with TMS is that it is quite complex to set up because you need someone who knows how the TMS works. You need someone who knows how to target the brain. So it's all skilled labor that needs to be paid to help stroke recovery. And one thing that is very prominent with stroke survivors is mental fatigue. So stroke survivors will usually not necessarily have the endurance to stay in for a very long session. So one of the idea of our submission was this kind of multimodal aspect of BCI, where we say, all right, we know people struggle with really intense sessions just after they had a stroke. So what if we try and minimize those sessions, which is also very beneficial for cost, and that is a huge factor for healthcare, obviously. So we try and minimize those intense sessions, but also try and give an option for participants to train on their own. So that's the EEG BCI aspect, where we say, well, we kind of know what we tell people to do or how we tell them to increase their response to the TMS and how to decrease the response. So what if we could create an EEG BCI that can recognize those two mental imagery states in their brain, those two mental states, and have them train that at home? So the basic idea is we get them in, we show them how it works, we try and make as little an effort as we can or as much as we can have them do in the hospital, and then send them home with a kit that they can train with alone at home. And obviously that also increases motivation and lots of other beneficial aspects. So the multimodal nature of it is that we use TMS and F, which is one part of the BCI, and also the EEG BCI, where we try and take over the training from this very labor intensive and also concentration intensive for the stroke survivor to something that they can set up and train as long as they want.
Yeah, thank you. And now, how this approach is different from what is currently being done in the same stroke patients?
So one of the main reasons that we try this approach is that stroke recovery or stroke therapy for especially for the return of movement or for motor rehabilitation is incredibly intensive, both in terms of how much time they have to spend with skilled people and also the amount of time that the patient has to invest. And the results are not mind-blowing. So for example, the best that we have at the moment, which is not a brain-computer interface, would probably be constrained movement therapy, where you put the healthy hand in a kind of oven mitten or a mitten that restricts movement and have the stroke survivor do lots of repetitions of movements with their hand. There's two problems with that. First of all, they need to train so much for improvements that are sometimes difficult to say if they come about naturally or if they are due to the training. So there's ambiguity about that. But also it is quite difficult for people who have no movement left to train, because you need to be able to repeatedly attempt movements to be able to train, to be able to do the physiotherapy. And if you can't move at all, then you can't do physiotherapy. So brain-computer interfaces here fill a gap that is very important in that they can kind of bridge the neural pathways or the spine in a way that can't really be done with anything else than brain-computer interfaces, because we can look at brain signal and give you a response or give feedback for the participant that they just don't have themselves. And the idea here is also that it might be able to bridge the time. As I said, stroke survivors tend to increase or tend to recover some movement naturally. But our idea is that if we can bridge the gap where they can't really move volitionally and give them feedback of their disaffected limb anyway, it might help them recover even more quickly.
Mm-hmm. Yeah, it makes sense. And I know that there are several systems for motor rehabilitation patients post-stroke. Some of them include electrical current stimulation and also 3D visualization of the hand. So several types of feedback are provided. What are other systems that are also using TMS? Are you aware of those, and how your TMS approach is different from those specific TMS approaches? If there are any, maybe there are not.
So there are a lot of approaches that are trying to do something with RTMS, which is repetitive transcranial magnetic stimulation, which typically is a lower intensity stimulation, but usually you use intermittent theta bursts. So it's a lot more stimulation overall, but just at a lower threshold. As far as I know, many of those systems have tried to target what we call the interhemispheric imbalance theory, or basically the theory that when you've had a stroke, you've had part of the brain that is damaged. And the theory goes that the brain is usually always inhibiting its counterpart on the other hemisphere. And when one part of the brain is damaged, it cannot inhibit the other hemisphere and therefore gets inhibited in return a lot more than it is used to. And the idea was that maybe if we can stop this inhibition, then we can enable a better recovery for patients. And then using RTMS, they would try to inhibit the healthy hemisphere or increase the excitation of the damaged or injured hemisphere, and therefore kind of restoring the balance that the interhemispheric inhibition theory predicts would be negative for the recovery of the patient. As far as I know, those have been inconclusive. So might be that we still need to work out some kinks, but also there has been a bit of critique about this interhemispheric inhibition theory, at least in a way to predict that it's not directly applicable to stroke. So that's about RTMS. As far as I know, there's not a lot of people doing stroke rehabilitation research with TMS. There is a lot going on about trying to predict recovery trajectories of stroke with TMS. As I said, one of the criteria is stimulating the motor cortex and seeing how the response works out to try and predict how the recovery is going to be. Because one of the problems of stroke as well is that since the stroke can take many different forms and shapes in the brain, the targeted, the injured area can be different and the symptoms can be different and the recovery trajectories tend to be quite different as well. So whenever you see a stroke study, it's always quite difficult to know, especially because we tend to not have a lot of people who have had a stroke in stroke studies. It can be quite difficult to know whether you were just unlucky with people who had especially bad strokes or people who had more light strokes, because it is quite difficult to predict the recovery trajectory. So there's a lot of research trying to analyze how to better predict their recovery, and there's a lot of repetitive simulation for both hemispheres. But as far as I know, using this single pulse TMS for BCIs has not been attempted before. Also, it might be because the way we construct our brain-computer interfaces, or the TMS and the EEG BCI, we are not necessarily saying that it is the TMS that will help people recover. We're actually saying we are trying to target endogenous healing processes within the brain. We're trying to get the people to use mental imagery or to attempt movement and then giving them feedback on the quality of this movement using the TMS. So obviously TMS might have beneficial side effects as well. Just for example, in a pilot study that my supervisor did in China, they noted that patients were extremely happy and motivated to see their stroke affected limb move when they received the stimulation. So that in itself may be just extremely beneficial because people see their limb that they cannot move themselves move again. So they know the potential is there. And so they work harder and are more concentrated during the therapy sessions. So that is a possibility. And then when we talk about research in brain-computer interfaces for stroke rehabilitation, we do actually see that there is a lot. So brain-computer interfaces have been used for stroke rehabilitation a lot, and they're actually quite good. They seem to be quite good, or at least they seem to not have any negative effects, which is also very good to know. But what is really impressive about BCI research is, or at least very interesting, is that they seem to be performing very well at stroke rehabilitation, motor rehabilitation, but they aren't quite widely used in hospital setting nowadays. And there are good reasons for that, because pretty much every research group has their own individual BCI setup. And also we don't quite exactly know how to trigger those endogenous healing processes of the brain. So for a healthcare provider, there is an insecurity about what kind of system to use, and there is an insecurity about how this system is helping the patient. So it's understandable why instead of using BCIs, most healthcare providers just don't. But the research is quite positive, and I think that within the next few years, we will probably have the first brain-computer interfaces for stroke rehabilitation reaching at least large clinical trials.
Yes, I really hope to see that. And now about the results of your study. Do we have any preliminary data?
Yes, absolutely. It's all preliminary results so far, but what we seem to be able to show is that people can still volitionally increase or decrease their response. So as I said before, due to the COVID pandemic, I am talking about results with healthy participants, not with stroke survivors. So within healthy people, we already knew that this TMS-NF could be used to help people increase or decrease their reaction to the stimulation. Now, this was made in settings where people would just increase or just decrease their response. So we didn't know how efficient it would be to train both at the same time. And we didn't know if people would be able to do it as fast, or we did just 2 sessions of TMS-NF. So that's quite a short training sessions for a brain-computer interface. And what we found is that people were actually able to do this quite fast. So even within the first of the 2 sessions, we can see differences in MEP amplitude or these muscle responses from the TMS stimulation. So that is very interesting. But also what we could show is that the group that does TMS-NF seems to be able to carry over this learning from this TMS-NF brain-computer interface into an EEG BCI. This also has wider implications for the BCI field because we are able to train on a different modality. That's another part of the multimodal aspect, and transfer those gains in one mode into another mode. So one of the other problems that the brain-computer interface faces for stroke rehabilitation is that it takes a while to learn how to control a brain-computer interface. If you're doing brain-computer interface research and you're strictly just interested in control, then you can have very specific paradigms which participants can learn to control pretty much immediately. Or you can use, for example, like P300 spellers, where you have kind of external events that kind of try and read what happens in the brain. And so if you're just interested in control, control is achievable easily. But when we talk about stroke rehabilitation, the main interest is not the outcome of the BCI control, but it is the rehabilitation aspect of the brain-computer interface. And therefore, usually there we tend to look at motor imagery or attempted movement. So we try and tell stroke survivors to try and move their hand. And then we work with the brain signal that this generates. And first of all, the brain signal of people who have had a stroke is different, but also it changes over time. So the idea of a multimodal BCI and the idea of the project also was to show that there is benefit to switching or accompanying the stroke survivors along his recovery trajectory. So at the start, when their brain signal or when their brain is injured and might have trouble to work with a brain-computer interface, we use TMS, which gives us a more haptic feedback, and also means that instead of using directly the brain signal as an input for the brain-computer interface, we use the reaction of the brain to the TMS simulation, so the twitch in the muscle. So that gives us a dimension of feedback that is also a lot more accessible for patients than the EEG, for example. So really the multimodal aspect stuff does a lot of different things, and there's lots of different research in brain-computer interfaces, which is fascinating.
Absolutely. And I'm very curious about that part that you mentioned, that you ask patients or potential participants to do at home. Yes, so to decrease that time that they spend in the lab settings. Can you provide an example what patients can do to make that part of the cortex more excitable? Yes?
Exactly. Yes. Typically, with healthy participants, you speak of motor imagery, where you ask them to just imagine because they can move. With stroke survivors, usually you would tell them just try and move because normally they have difficulty moving. So you can work with direct outcome that you're trying to improve, so the movement itself. And the idea of the multimodal BCI was we have people train with the TMS NF for all the benefits that I've listed before. So it's a haptic feedback. The TMS might have beneficial aspects, and it's quite easy to learn the TMS NF system. And then once they can do that, we can send them home with an EEG BCI that try and do the same thing as the TMS NF, but without the whole TMS part. So motor imagery can be decoded by an EEG. The very typical Graz BCI is actually, I think, more than 20, 30 years old, where people are just imagining to move their right hand or moving their left hand, and this can be done quite reliably. Now, with stroke survivors, obviously, you're not aiming for control, you're actually aiming for motor improvement. So all you would try and ask them to do is imagine movements and then a rest trial. And the BCI's job in this case is to give the participant feedback on how well he is doing his motor execution or his attempted movement. And thanks to the pandemic, well, I shouldn't say that because that was horrible for everyone, but one of the positive aspects for our research with the pandemic was that we were able to test this separate BCI phase of the multimodal BCI and send some easy to use Bluetooth dry electrode EEG kits to people at home. Again, healthy people. And we asked them to set it up. We sent them links to the software. We instructed them with Zoom on what to do and what to expect and troubleshoot it with them. But then they trained on their own. I think there's not many people who have attempted this before because it was quite difficult as well to coordinate with all the participants and get all the software to work. But in the end, it did work. So people were able to get an EEG BCI sent to their home, set it up, get it to work, and then also be able to control it with a control scheme that was not focused on the control outcome, but that was really the same that we do for TMS and F. So we try people to increase or decrease their reaction to the TMS, which we do by telling them to attempt complex and forceful movements. And we told them to do the same at home. So imagine complex and forceful movements. And the BCI could pick that up and give them feedback on how they were doing. And they did improve over time. So we could show that at least in healthy people, both aspects of the multimodal BCI is possible and multi-stage as well.
That's a great approach, and it's so good to see that this approach worked when you send the devices to people and you made it possible to work. Because I think it's one of the major problems that people still list that simple BCI devices work in the lab, but they don't work in the real life settings like at home. So you were able to manage that, and it shows that in general it becomes possible. So that's great to know. And because you mentioned healthy people and they can elicit change that is detectable, is there any possible application for athletes also to somehow improve their motor function, outcomes of the movements using this type of BCIs?
Whenever we talk about brain-computer interfaces, we're really talking about kind of bridging the gap between the brain and whatever you want to happen in the environment. So in the case of, for example, the P300 speller, you're trying to give people the option to write things without having to use their body, or just their brain. Now, when we're talking about athletes, they usually have access to their body in a functional capacity. And that means that they can just train whatever they want to be doing. This is something that we see in BCI literature as well, people being very focused on control and what we can do with BCI instead of thinking how it can help people. So with athletes, I think it's probably just better to train. But with professional athletes, there might be a range where you say, my physical body is extremely tired, but I am still mentally able to train. And that you can do. And I mean, there's great stories about the Olympian swimmer, Michael Phelps. He has won many medals. And he said that one of his bedtime routines is he goes for a swim in his head before he goes to bed. Or one of his strategy of improving is mentally thinking through a tournament situation. And that is definitely things where we could try and analyze the signal in form of the BCI and get them to try and imagine it more realistically. We could probably target somewhat the sensory cortex, where people feel how they imagine or feel the things they imagine, and try and give feedback on that, for example. And that might be able to help an athlete who is struggling with the imagination part and is too tired to train, but still wants to train. So there is a possibility for that. But especially in stroke rehabilitation, I think as soon as you have the ability to train the movement you're trying to improve, the direct training is likely to be better than the brain-computer interface. But the reason why the brain-computer phase is so important and interesting is that many of those participants regain this kind of movement only after about 6 months. So that's 6 months where they cannot move and they cannot train and they cannot start their recovery process. This leads, I think, to a lot of mental frustration and fatigue that we might be able to address and improve outcomes with BCI technology.
Yes, absolutely. And I remembered about also some cases of athletes who had some type of injury where they couldn't perform the actual movements and train. So there are cases of when they use their imagination and it supposedly helped their recovery and just not stopping the training. So that might be a time where BCIs are also come in and help. Okay, very interesting. Now, in every project, there are happy stories when we get results and everything goes well. And of course, there are challenges. What were the challenges in your case, and how did you overcome those?
So many challenges. I don't even know where to start. One of the biggest challenges was setting up the correct measurements for the electromyographic activity. One of the problems with these MEPs, the motor evoked potentials that you get when you stimulate someone with TMS, is that the background muscle activity of participants is predictive of how big the response is going to be, which makes sense. If you pre-activated signal, the response is going to be much stronger than a previously inactive system, right? So this is kind of what's happening. If you're flexing your muscles and you get stimulated, the response is going to be much higher. So we needed to find a way to make sure that the people would not be pre-activating their muscles. And the TMS and F part has a kind of a game-like system where we constantly measure the muscle activity. And if it is too high, the participant will see some red traffic lights and they will not be able to proceed, and they have to relax until they can proceed.
Mm-hmm.
Now, setting up the system was complicated. And one of the not scientifically interesting, but funny stories was for a while we couldn't figure out what was creating noise in our EMG signal. And I would wire up myself, and then I would try and relax in a chair, and I would see huge muscle activity. And I knew I was not moving my fingers. So I was trying to figure out the source of that. And it got so far that I looked up on YouTube how to build Faraday cages, which got me into the survival prep, very much conspiracy theory part of YouTube, just because I tried to find out how to build Faraday cages. And I pretty much wrapped the whole testing room in tinfoil, just trying to figure out how to eliminate this erroneous signal I was seeing. And in the end, it worked. And we built, but we noticed it was the transformers from the laptop chargers that were creating a lot of interference. So we just put them in a small Faraday cage, which was also a lot better for fire safety than having the whole room in tinfoil covered.
Yeah, those are amazing stories. And, this is something that you cannot read in the article, but behind the scene experience, it's amazing. Thank you so much for sharing. And you learned a lot during this process.
Absolutely. I know how to build a Faraday cage. That is not something I thought I would know how to do.
Yeah, absolutely. Wonderful. Now, let's get a little closer to the BCI Award. Why did you decide to submit your project?
My lab was at the time quite small. So it was just me and my supervisor when we started, which was great for me because that meant I could take on a lot of responsibility and have ready access to my supervisor. That was absolutely fantastic. But also that meant that a lot of the work that we did kind of went unnoticed because neither me nor my supervisor had the energy after a full workday to also promote what we did. So we were looking for ways to kind of reach more people about what we were doing because we thought that we had something that was quite significant on our hands, both with the TMS and F, so connecting the stimulation, building a brain-computer interface that is not necessarily dependent on the brain signal itself, but on a brain derivative signal or brain-derived signal. Mm-hmm. So we were looking at opportunities to give talks and presentations, and we stumbled upon the BCI Award. And we just thought that this was kind of exactly what we needed. And turns out we were right.
Yes, absolutely. And congratulations on your successful submission. What advice is that you can give to the people who are planning to make a submission for the BCI Award, and maybe even for those who are on edge and maybe are thinking, maybe my project is not good enough still for BCI Award submission. Maybe for those as well, you can say something that would encourage them.
Yeah. I think the most encouraging part is that whenever you don't try, you have lost automatically. So even if you think that you're not going to be able to do it, or that you think that your project is not special enough, if you think like that, you've already lost. So instead, try and figure out what makes your project special, because chances are if you're working on something, you have a passion for it, especially in academia, especially at our level. It's really hard to find people who are not feeling deeply about what they do. So try and convey those feelings about what makes your project special, and just try, because if you don't try, you've already lost, and it's more fun to not lose. I would say one thing is about trying to figure out what makes you passionate about the project. I know, for example, that for me and my supervisor, it's different things. I think she's really interested in the stroke part. I think transcranial magnetic stimulation is just really, really cool. And that's the part that fascinates me the most. And brain-computer interfaces in general are also really cool. I think that's how I got interested in the position in itself. Is I was thinking that brain-computer interface might be the next big thing. Back then, when I was thinking that, it was more about the next big consumer application. I think now that I am in the field, this is definitely not the case. But I think for stroke rehabilitation, we might be on the verge of having a lot of success with brain-computer interfaces.
Yeah. How do you see the field of brain-computer interfaces, maybe for stroke rehabilitation specifically, if you would like just to concentrate on it, 50 years, 100 years from now, how would you like to see it, and where do you think all this field is heading?
As I alluded to before, there's lots of different fields of brain-computer research or brain-computer interfaces. And I think for stroke rehabilitation, we have three problems to solve. One of them is trying to get some standardized protocols, which might be helped by the second thing that I'm thinking about is trying to understand how the brain-computer interface can help with stroke rehabilitation. By that, I mean what biological mechanisms in the brain are enhanced or improved with the brain-computer interface that might help stroke survivors regain their motor movement. I think if we figure out how those improvement mechanisms work, it will be easier to have very standardized protocols, because then we can start improving efficiency. And eventually, once we figure something out, it will all move in the same directions and get more standardized. But right now, we're more in the exploratory phase where we're stretching out feelers in each direction, trying to find something that is unique and works really well. And once we have found that thing, I think it will be much easier to push forward in the same direction and get more standardized protocols. I think those two things will help tremendously, because they can increase the mental safety for healthcare providers, that they know how the BCI is helping, and maybe they can also know when it is not helping, know when not to use BCI. And at the same time, there's not one BCI per research group, but there's maybe one specific. You were talking about functional electrical stimulation BCIs. So maybe that can be like an umbrella group for BCIs that work well, if we ever find out that this is what it's working. So there's the standardization of protocol, but also the understanding of what works. And I think the last part of brain-computer interfaces for stroke rehabilitation, but also in general, that is really important to do, is to not forget that at the end of the day, it's a human using the brain-computer interface. And there's a lot going on psychologically when you are interacting with something, even if you're using your body. There's just a lot going on. And there's some very interesting research by the INRIA group in France, where they just try and figure out how to make better BCIs for the user. One of the things they know, for example, is that if the feedback is closer to things that we know how to perceive, it's easier for us to accept the feedback. So if you get very abstract feedback, that tends to be slower to learn. And I think one of the cutest experiments they've done is they've had a little robot convey the results of the feedback to the participant. And they also show that getting this more human-like interaction helped a lot with improving control over the BCI. So this is a more control-focused group, less about stroke rehabilitation. But yeah, when we do think about brain-computer interfaces, it is important to not forget that there is a human there that needs to learn how to do the things. And it's not just an expensive tool to project from the brain to the hand, but the human has to do some work as well. And if we can explain better how to do the work, or if we can improve the way feedback is given about the work done by the human, this might be able to go a long way as well.
Yes, absolutely. Improving designs, yes, of the BCI systems to improve the experience. Yes. And now that you talked about the future of BCIs, what are your future plans? How are you planning to continue the study, or, do maybe something completely different in the field?
Absolutely. I am now trying to get the non-preliminary version of the results, so the actual results, and trying to publish those results, because we have also found some quite interesting results in the EEG range of the multimodal aspects. So I'm really excited to publish those and get feedback from the community. For our lab, I think the next important step will be to test all these hypotheses in the hospital. So as I was saying, the lab now currently in Dublin is working frantically to get into the hospital. They are in the hospital. They have run some pilot tests in the hospital. So data collection should be starting any day. And I think once we have data with actual stroke survivors, that is going to lend a lot more credibility to the idea of multi-stage and multi-phase BCI.
Yes, thank you. And I wish you all possible success, of course, with these studies and waiting to see the results. By the way, you mentioned one of the reasons of applying for BCI award was to gain some visibility. So did you notice any changes in visibility after your successful submission?
Absolutely.
So what was that?
I mean, one of the things was just telling people in our community that we had applied for the award and gotten nominated. And that was already a huge amount of feedback that we gotten. And I think that made a lot of our colleagues not just talk about what we do, but also be reading what we do or be very interested in what we do in a more visceral sense. I have gotten personal messages on LinkedIn from people congratulating me and asking if this therapy was already available for stroke patients. So unfortunately, this was not the case, but I was very moved to still get asked on LinkedIn about that. So that was a personal success story.
Yes, absolutely.
We did also get some quite positive response because he sent some very nice plaques that we hung outside the lab, and people did talk to us about those. And so there's lots of personal interaction that we got, and also online. When we announced that we had won, we got quite some positive feedback on Twitter, which obviously is the end stage for all research, right?
Yes. Did you receive any requests to join your lab? Did you get more students to your team?
Well, we did get a lot of applications for students to mentor for their final year projects. They didn't say it was because of that, but you never know.
Absolutely. And maybe also you can mention some words of wisdom or give some suggestions to people in the psychology field who are interested in pursuing work with the neurotechnology.
Yes.
So, what helped you as a psychology major to do this work? Maybe some skills.
Yes. So I think my main encouragement would be to not be afraid, because it is such an interdisciplinary field. No one is an expert at what they do, or everyone is an expert at exactly what they do, but not much else, because there is so many different aspects. Talking about my project, there's stroke, there's all the tech involved with the TMS, there's all the tech involved with the EEG, there's all the tech involved with bridging both technologies together. And then there's also not forgetting all the, as I said, like the human part of the brain-computer interface. So really, there's so many things that if you just focus on something, you will be able to contribute productively to your team. And as a psychologist, my course was not split between people who wanted to do research and clinical psychology. So I got quite a lot of the clinical sides, and a lot of the people in my course also got a lot of the science side. And I think if you've got the science side, which I think in modern psychology courses is extremely pronounced, with lots of emphasis on understanding how statistics works, understanding how to create good experiments. Those are extremely valuable research skills that someone who has done engineering might not have. That is not to say that engineers cannot do science, of course. It's just that we are trained from the very first lesson of psychology in understanding how to design experiments and how to test statistics on those experiments, which also can get quite complex. So if you do come from a background that is more computer science heavy, for example, you might lack statistical expertise or expertise on how to do experiments, which as a psychologist you have. So if you're in psychology and you are interested in neuroscience, just start to look around for opportunities at the university where you might be able to contribute as a research assistant, or if it is within your means or you have access to the Neuroscience Society, you might be able to just take a kit like an EEG kit and try and make it work. Try and make it work with yourself. That is not as hard as it seems. And once you get into it, this kind of tech savviness of just being able to bridge gaps between technologies is something that is extremely valuable as well, and does not necessarily take a lot of tech skills itself. I, for example, had to wire up the TMS machine with a national instruments board to make the communication happens between the machines and the computers. And when I looked at that, I was completely overwhelmed because this is not something I learned as a psychology student. Turns out, though, it's just about plugging in things and then being investigative. Like, it didn't work at the start. And then I investigated and I figured out what was not working. And that was research and not tech. So there's lots of research skills you get in psychology, which are extremely valuable to the field.
Yes, absolutely. And what you said brings me to the question of making the impossible possible. So, what were the things in your work that seemed at the beginning as impossible that you've made possible, and how did you do it? So, what would be your main piece of advice for making impossible possible?
I think the best way to make impossible things possible is to not think of them as impossible things, is break down the goals you want to achieve and then just go from there little by little. I think one of the main challenges we try to address is to bridge this kind of gap where stroke survivors cannot train, right? And when we use TMS NF, we get a signal that is quite handily available because we know from the research from the stroke recovery subject that TMS responses are available in stroke survivors. So there you've got suddenly a brain signal. So now you've got a brain signal. So how do you build upon a brain signal? Well, you try and figure out whether you can do something with that brain signal. And it turns out we can get healthy participants to increase and decrease their response to this TMS stimulation. So suddenly you've got a BCI. And now the idea is that, well, how do you construct a BCI that works well enough that you are able to put it up in a hospital and try and see if it helps people with stroke? So yeah, don't think of the impossible as the impossible. Think of the impossible as the not yet possible.
Very good. Yes. And break down everything into small tasks. Yes. And just handle one by one. Excellent. Can you share with our listeners where they can find more information about the research you do and what would be the best way to connect with you if they have some questions or maybe even want to join your lab or something or do a collaborative project?
Absolutely. We are happy with anyone who tries to contact us. So our website is translationalbrainhealth.com. On LinkedIn, my name is Colin Simon. You will find me if you look for me at Trinity College Dublin. My supervisor is Dr. Kathy Ruddy, who is also at Trinity College Dublin and also has some strong ties to the Belfast Queen's University. You can find us on Twitter as well. My handle would be C Simon, if I recall correctly. And you can always reach out via email, which would be csimon@tcd.ie.
Okay, and we will add all this information also into our podcast notes so that our listeners can take that information right from there. Wonderful. So thank you very much, Colin, for this very insightful conversation. I really appreciate you joining us and talking to our listeners about this amazing neurotechnology stuff. I wish you all possible success in your future endeavors. As we end our podcast, anything you want to share with our listeners? Anything else you want to say or, any advice you want to give?
Well, first of all, thank you for having me here. It was an absolute blast. I had a very good time and it's been an honor to be here. And I am really looking forward to see this year's applicants to the BCI Award. I think last year there was some stuff that even me being completely in the field, I was completely blown away by what other people have achieved. So that was absolutely impressive. And I'm really looking forward to this year's applicants and entries. And yeah, everyone just stay at it. We'll figure out how to make this work.
Yes, we will. Thank you so much. Are you a fearless pioneer in the world of brain-computer interfaces? Do you have an amazing project that's pushing the boundaries of what's possible? Then we want to hear from you. The International BCI Award is one of the biggest and most prestigious awards in the BCI world, and the deadline for submission is September 1st. But don't worry, you don't need a top notch budget or equipment to be a nominee or a winner. All it takes is a great idea and the determination to make the impossible possible. So, submit your project now at bci-award.com or find the link in our podcast notes and join us on this incredible journey to explore the world of BCIs. And make sure to listen to our upcoming BCI Award Neurocareers podcast series for tips and tricks on creating a successful submission. Who knows? You might be the next nominee or winner of the International BCI Award and proudly showcase your nomination on your resume to impress potential employers and establish a successful career in neurotechnologies. But don't stop there. If you're looking for more guidance on succeeding in neurocareers, book a free consultation with me, your podcast host, Dr. K, at the Institute of Neuro Approaches. So, what are you waiting for? Let's make the impossible possible together.